So, good afternoon, ladies and gentlemen, and thanks for waiting. So, our speaker today is Dr. Allolio from the Mathematical Institute of the South today. So, Christoph has been the head of the group of biomembrane modeling for many years, and I think it's good to have a talk, I guess the first talk from some biomathematical environment. So, thanks a lot.
Thank you for the kind introduction. I think it's not quite true because I have been here before and it was about also biomembranes, but more in the context of the Helfrich Hamiltonian, right? And but since this is the Continuum seminar or the Nečas seminar for continuum mechanics, I'm going to provoke you first of all a little bit and say, you know, like the most important thing is actually that everything is made of atoms and hence particles. So this is what Richard Feynman thought. And what is a little bit special about my basically approach to, or our approach to this continuum modeling is that I'm originally basically a particle guy, and a lot of the parameters for the continuum models that I use are basically taken from detailed particle-based simulations. So, and these particle-based simulations typically are using Hamiltonian mechanics, where you have, or yeah, just Newton or maybe Newtonian mechanics, where you just have some potential U, which is rather complicated and describes all the interactions between the particles. So I don't want to go into too much detail about that, but what you may want to know is that basically you can imagine these things as classical particles. Our atoms are classical particles that are connected with springs and, you know, have some electrostatic partial charges and some dispersion interactions. And basically all of this is determined by classical, like by established parameters. I'm not inventing any parameters. These parameters are in well-known force fields that Baird chemists developed. And what makes it somehow interesting is that if you run these sort of, you know, trajectories of your entire systems for a long time, you obtain probabilities, and from these probabilities you can obtain free energies. So if I show you some free energies, they will be obtained from a long particle-based trajectory where I calculate a distribution function and then basically assemble it and then to obtain these free energy calculations, right? But again, this talk is about what biologists would call, or microbiologists would call, mesoscale structure. So here you can see basically a droplet of blood under an electron microscope. So these little sacs here, these are red blood cells. These might be, you know, like other types of cells, white blood cells. And basically what you can see is that the structure of the outermost layer of these things is given by a biomembrane. So this is what you see are biomembranes, and if you cut them open, you will again see biomembranes. So here this is a Golgi apparatus, which is an organelle inside the cell. Here a chloroplast, which does the photosynthesis, a mitochondrion. All of these things have internal membrane structures, as do viruses, right? So here you can see a little bit of HIV viral budding. Again, you have some scaffolding and some outer membrane that is being basically cut off. And of course, what you have is basically not only the membrane, but lots of proteins also that sit on the membrane, and maybe some underlying structure as well. But I'm showing you this slide because I think what is like if you want to look at, you know, subcellular structures, it's a good idea to start with membranes. And when you want to model such membranes, you have a bunch of choices. And the straightforward choice, if you are a particle type guy, is you just assign a particle to every atom, and use some sophisticated interaction potentials, and then you can model basically one protein on a slab of membrane. And that's of course not enough to give you these organelle shapes, but it's fairly accurate. And then you can go and you can say, okay, we group those atoms, those things into effective beads. We make effective particles. Then you get what is called coarse-grained molecular dynamics. You lose some of the specificity, you lose some of the accuracy in your description, but you will be able to describe such systems here, which might already be important, you know. But of course, they're just a pimple on these large-scale structures that you've seen on the electron micrograph. And then finally, you can use continuum models, right? Here you have to imagine these things as a mesh, and then you have somehow a continuum without atoms, which is basically scale-free. So obviously, what would be great would be to have somehow local parameters from the atomistic simulation and proper long-range forces by extrapolation, and then stick them into local continuum parameters, basically, like effective coefficients for maybe elasticity, structure, or charge. And then you might be able to get the full accuracy. So, I mean, if you look at the lipid membrane, you can imagine it as a bunch of molecules which have basically heads which are exposed to the solvent, and these tails which are fat. Yeah, so a membrane bilayer will have a mirrored structure of this type. And if you want to describe a monolayer or a bilayer, you can use this so-called Helfrich-Kosloff Hamiltonian, where you have here the mean curvature, an intrinsic curvature, which is a local parameter, and the free energy per surface. And here this kappa is your bending rigidity. Then there are two more coefficients, and this is the Gaussian bending modulus, and this is a kind of modified version of the Gaussian curvature, which we know is, if the membrane is closed, it's a topological invariant. So we usually do not care about it, but we will see that we care about it anyway afterwards. And then here is a little bit of a special thing. So you may have noticed these tildes here. So the tilde normally H would be your mean curvature, but the tilde means that it's actually not the normal mean curvature, but it's not basically the covariant divergence of the normal field, but of the director field. So you have here the director vectors, which are basically the directions in which the lipids point. And if they do not point along the membrane normal, then you get a third thing, which is the tilt. And so this is this T, and it has its own modulus. So this is our Hamiltonian, our free energy functional that we want to minimize, or that we want to look at. So again, for this, we need the local coefficients kappa, and the local coefficients can be obtained by the following trick. We run very small scale molecular dynamic simulations and just let the lipids wiggle, and then from this wiggling, we obtain the tilt. But the tilt basically couples into the bending, and so from the divergence of the tilt on the flat geometry, we can get the bending rigidity, and of course we can also get the tilt modulus. So this is the first trick, and the second trick to obtain local coefficients is to use this moment expansion of the free energy. So the bending moment, so derivative with respect to the curvature, can be shown with some modest assumptions to give you the product of kappa and JS as a function of the first moment of the lateral pressure. So what we need is a local resolution of the lateral pressure, which is essentially a part of the stress tensor of the thing. So what we to translate from the particle-based simulation to the continuum, we require a kind of through space local stress tensors. So the stress tensor has a kinetic component, which is always the ideal gas, and a potential component. And this potential component basically depends on the mutual forces between two particles, but you basically, as they go through space. But the force line, you can choose. So you have here a free choice of a contour. Actually, the freedom is even a bit higher. And we choose here some very unnatural contour, basically a rectangle, which allows us to calculate these interaction forces using particle mesh-Evans method. So we can do it in a periodic system, and that allows us to take care of the long-range electrostatics, which we need. So this, then we use a force decomposition for the many-body terms, and then after sampling, we obtain basically such profiles here, which give us the lateral pressure distribution inside a membrane simulation. And from this, we can obtain basically the coefficients of the theory. And this is all available online. You can download it and play with it if you want. So again, the first application of this was to, right, what do we need to take care of? If we want to model arbitrary membrane structures, we have to take care of the local elasticity, which we did, but there may also be topological changes. For example, two membranes might basically fuse, right? This is one of them. A membrane might rupture, or of course, you can have complex mixtures on the membrane. So all of these things we have to take care of. So I will just go on. So to do it, we basically obtained our local coefficients, and then we made basically like in a cylindrical coordinate system, we solved this Helfrich-Kozloff Hamiltonian. And here you can see to some extent why we needed this tilt degree of freedom, because here where the membranes basically touch, here the monolayers touch, they have to be, you have to set the boundary conditions so that basically there is no discontinuity, at least in the director field of the membrane. So this allows you to build a fusion stalk, then you can minimize it, and then we can look at how the coefficients behave and how the minimal energy behaves as a function of the adsorption of, for example, calcium or the lipid composition. And so we were able to see that, for example, the lipid PIP2 in presence of calcium and the lipids PS and the mixture PEPS have stable fusion stalks or almost stable fusion stalks. And these are experimental lipids that you can actually fuse with calcium. So this was a test against experimental data. And then for holes, like for making pores, we also showed that there is a very good correlation between basically there is a so-called pre-pore, and this pre-pore we can predict, or the energy of the pre-pore we can predict using the tilt modulus, and the line tangent of the ruptured membrane we can predict using the product of curvature and elasticity. So this came out this year. So we can do this, and of course now we have to also take care of the mixing terms. So for the mixing terms, we just calculated a bunch of different lipids, their coefficients for bending rigidity, for spontaneous curvature. Then we calculated explicitly some mixtures and tested those then against the mixing terms. That, like, what would we get if we took the values from the components and mixed them, and we get pretty decent, agreement, I would say, between the prediction from the components and the direct mixture. Okay, so that means we can now simulate arbitrary lipid mixtures. Now we have to also be able to do arbitrary geometries, because you saw what we did before was just, like a cylindrical coordinate system. You want arbitrary geometries and arbitrary, fluctuations in the system too. And to do this, we basically use what is called a dynamic triangulation. And that basically means we have somehow a mesh, in this case, a mesh with normals, and we just kind of manipulate the mesh so that it is dynamic. And this mesh, on this mesh lives an interpolant, and this interpolant is constructed by just requiring that it is basically orthogonal to the mesh normals. So you do this for an edge, and then you assemble the edges, and you get an interpolant. This was invented by Takashi Nagata, and it is not obviously tangent continuous across the edge. So that's why it's just quasi G1. So to get it tangent continuous, one has to apply a penalty function. It has also another problem that it is not sufficiently flexible because it's just quadratic. It is constructed by basically requiring this and then using a pseudo inverse to solve this underdetermined system. But it's not good enough. So we had to supply it with an estimate of the binomial vector. Then you can again solve the pseudo inverse, and you will no longer get pathological cases. Ask me later if you want to know more about it. Any case, so now we just have to, with this discretization, we minimize this functional more or less, and we obtain basically the known solutions for the Helfrich theory. So this works. This diagram shows you here the energy, a reduced energy as a function of the reduced volume. So the reduced volume is just basically here a reference to the sphere, unit sphere. So that's a correct result if you compare it with the literature. And of course, you also tested the numerical performance of this discretization, so it works reasonably well. And you can if you want, look at it a little bit like this. This is here a transformation. So I will tell you about how we propagate the mesh in a second. So this is how we get from a discocyte to a stomatocyte. It's not showing all of it. And so the way we manipulate the mesh is simply using Monte Carlo moves. So we have different Monte Carlo moves in the system. One just moves a vertex, another one moves a normal, another one flips an edge, and yet another one transfers lipids. So we have also on these faces, we have a fixed lipid composition. Okay, this is basically it. And then we can use the Metropolis Monte Carlo algorithm to ensure that we have a Boltzmann distribution on our, at least in the stationary state for our mesh geometries. And that means that we include all the equilibrium fluctuations of the system, including composition fluctuations. So we published this, we made some nice pictures, and you can download it. And what might be interesting for you, if you are interested in such things, is, it's a numerical tool. You can use it also to, it supports many different boundary conditions, flat meshes, and somehow, like gradient orientations, but it also allows you to control domain formation. So you can have non-ideal mixing and domain formation in it as well. Okay, so now let's apply all of this technology to some real-world problem, and this real-world problem is now cell-penetrating peptides, and this is being done by my current PhD student Yovi Koikara, and we also already put this out as a preprint. Okay, to introduce you to cell-penetrating peptides. Cell-penetrating peptides were first discovered in HIV research. They're just fairly short peptides, but they have a large potential for drug delivery because as you can see, these are, fluorescently labeled cell-penetrating peptides, and they enter just about any type of cell. And they can also carry large cargo in just about any type of cell. And in fact, they can do it even without cells. They can enter even just pure membranes, which means that we should be able to model them without having to model the entire cell. And the way people used to think that works is that you somehow have, here your cell-penetrating peptide, and it goes, right through the membrane, and then triggers something that pulls things through. But this makes no sense because, as you saw, you don't need any transport mechanism. So, in fact, another thing about cell-penetrating peptides is that they are highly charged. So if you use, this is a chemical structure, don't be afraid. This is just an amino acid, and it's which will go into the peptide. So you link the peptide this way, and then here on the side, you have a charge. And you can have either this positive charge or that positive charge. And basically, otherwise there is no big difference. But if you have this arginine and you just put it into like a long string, it will be a cell-penetrating peptide. If you have the lysine, it will not be a cell-penetrating peptide. So it's something chemically specific. This is one thing to remember. And the other thing is that, again, there is a lot of different mechanisms that were proposed in the literature, how these cell-penetrating peptides enter cells. And I mean, I already talked about this direct translocation mechanism. Other people think that it might just dissolve the membrane or go into some inverted mast cell, but it's in general very confusing. However, a great deal of these mechanisms have in common is that you form some sort of invagination at the beginning of the entry mechanism. This is often supported by active transport proteins, like this football cage here that self-assembles, but it sometimes also works directly. So if we believe in our non-protein supported cell-penetrating peptide mechanism, it should be something like this. And in fact, after the cell-penetrating peptide enters, it ends up in some sort of endosome, which then again has to form this type of structure to escape the cargo into the cell. So this is microscopy data from someone else who directly observed this for some cell-penetrating peptide. And you can already see here what they postulate, that you have basically the cell-penetrating peptides aggregated around the neck and in this smaller vesicle, basically a form of curvature sorting. So if it's curvature sorting, we can use our tool to kind of describe it. We can extract all the coefficients of the model from the particle-based simulations. And then we just have to find our free energy. So this will be our usual Helfrich energy, this time without tilt, we don't need it. Then we add some binding free energy, some chemical, which just depends on the peptides. So we have to somehow find this from solution, from the simulation. Of course, kappa we have to find from the simulation JS and the J kappa J bar as well. And then we just add some ideal mixing terms and the mixing terms from that we validated. And here you have basically stretching energy, and in particular, this comes from the osmotic pressure. So when you have a closed vesicle and you with a fixed concentration in it, and you shrink the volume, you have to work against the osmotic pressure, and this is what this gives. Okay, so we calculated here with the binding free energies for R9, our cell-penetrating peptide, on all the different components, and then we calculated the local stress, giving us the JS and the kappas. And then we, of course, had to also think about how the proteins, the cell-penetrating peptides interact with each other on the surface. And for this, again, we did large-scale simulations on a flat surface where we saw that they just repel. So this is a so-called pair correlation function. And if it goes above 1, it shows you that they kind of attract. If it goes below 1, it shows that they repel. So you see it just kind of goes up straight to 1 as if it was just a size exclusion. So we treat it as a size exclusion, and then we calculated the binding energies to all the lipids, and we adjusted the area that it takes on the lipids to reproduce basically the excesses of lipids around this R9. So if you wonder what this thing here is, why does it bind to R9? That's because DOPS is negatively charged. So this is just electrostatics driving the sorting here. And then we had to go and plug in something for the Gaussian bending rigidity, which we did simply by expanding the thickness of the membrane and using the spontaneous curvature. And then finally we get the results for the thing which tell us that indeed such invaginated structures are stabilized by R9, the cell-penetrating peptide, but they do not occur without the peptide, and they do not occur with K9, the non-cell penetrating peptide. So the model, like the way these structures form, is by curvature sorting. In fact, the system sorts, the peptide sorts to indeed exactly to this invagination and to the neck. So to the C zone and the B zone, right? The C zone is pure negative mean curvature, and the B zone is negative Gaussian curvature. So this is also in agreement with what people have postulated. And we also see that basically the PS, so the negatively charged lipid, follows the R9 because we implemented this interaction potential. And that's basically, and then here, this is the direct confirmation by electron micrograph. So people made exactly this type of vesicles, and we obtained these type of structures in collaboration with the Jungwirth group, and that these structures basically look identical to those that we calculated without any input from experiment. Of course, it's more complicated than that. You see there are more complicated structures, also aggregations of vesicles. So this we still have to do. So this is the first part of the talk. And if you have time, I will also talk about the second part, which is E. coli and E. coli cell division. So this is E. coli. It probably lives on your hand. It lives on your salad. You don't like it, but it's there. And we also already, this is now, we will soon get our reviews from PNAS for this. It all started, right? You saw I did this fusion, and then Luke Chow, my collaborator in biology in Massachusetts General Hospital, said, hey, why don't you do E. coli, right? E. coli, that's just like membrane fusion somehow in the reverse, right? It's like this. You have here this constriction phase somehow in the beginning of the division, and then you have a septation phase where you have, like some septum growing, and then you have a splitting. This should be easy. It's just like membrane fusion, but of course it's not, because basically it turns out that what carries the load of the bacterium is not the membrane at all. It is what is called peptidoglycan. So you have actually a bunch of cross-linked plastic in between two membranes, and this cross-linked plastic is, of course, it is not fluid at all. So it has to the basically mechanism of the division cannot be the same as a fluid membrane fission. Yeah. So what you have are cross-linked chains, and these cross-linked chains must be somehow dissolved and reorganized. And of course, in the textbook, it all looks very neat. It looks like you have, some very, very clean fiber orientation. But in fact, the fibers are not oriented, barely oriented at all. If you look at it under the microscope, it's just like there's barely an orientation. And on top of it, now you have a fairly complicated, synthesis machinery that basically, indeed, here this is your cross-linked polymer that is being basically eaten by amidases, which destroy the cross-links, and these destroy these naked PGs, peptidoglycans, polymer strands, attract a production machinery, which then recross-links it, but also increases its volume, so to speak. So we had to model that, yeah, and of course, and then there's another important part, right? You may wonder, how does the bacterium know that it should constrict in the middle? What is the force that drives this? And so there is some force, but it's a very small force, and this force is generated by these so-called FTSZ filaments, or the FTSZ ring, which kind of constricts at the interior membrane and then gives a slight force on the PG, which is nowhere near enough to deform it significantly. So if the force is not really sufficient to deform the material a lot, how can that be? I mean, first I tried it with a soap film. It looked kind of promising, but of course, again, it's cross-linked. So if it looks like a liquid, then maybe it's for the same reason that, for example, this pear here looks like a drop. It's even though it's made of wood. So you have somehow a growth that translates these very small forces, this very small stress into fixed shapes. And so we postulated that the growth must follow stress, and then we just had to define the growth somehow. So we used, I guess, this Lagrangian framework. You just have, right? I'm sure you know this from elasticity, right? You have your deformation gradient, and then we introduce the morphoelastic splitting, where you have the elastic tensor and the growth tensor together, just like in elastoplasticity, except that your determinant is, of course, not always 1, but it changes. Okay, so this is the basic setup, and so you have basically here your stress-free reference configuration, then a growth mapping, and then from that the elastic one. So this is kind of a little bit messy, but this is the theory of morphoelasticity by Alain Gouriellery, and this was done by Petr Perlich, essentially the work here. So Petr used an elastic energy functional, which basically includes, which is this polyconvex ansatz here, because to make it extra, mathematical, that's why we still haven't gotten our reviews back, right? Why would anyone? But I mean, of course, it guarantees minimizer or whatever. And here, then you have here the anisotropy from the fibers, right? So we pretend the fibers all run around the circumference of the bacterium. And yeah, that's about it, right? You have an isochoric and part, so it's split as well. And then to make the biologists believe us, we also did a lot of literature research to find out what should the parameters of this elastic energy be. So it turns out that if we to find this out, we basically combined turgor pressure data with strain data, which was measured by someone else, and then the Young moduli data, and then we kind of mixed and matched it and checked where things could plausibly be true. So which realistic values of turgor pressure fit to which realistic values of strain, and then we could kind of narrow it down, because as you see, there are orders of magnitude of difference between the elastic parameters reported in the literature. Okay, so this it sets up the elastic functional. Then we just made, this is like the setup of the system. So again, it's a cylindrical cylindrical system where we just apply a pressure for the zeroing force and a turbo pressure on the inside of the material. We model the peptidoglycan as a real 3D elastic material, hyperelastic one. And then, yeah, so then we take the other following inputs. So we have a global mass rate, which was measured by our collaborators, which as the cell's PG production. And we have a growth zone, which is predicted by the arc length, the distance to the middle, which at least we have some sort of plausible, limits for. And then we have the remodeling rate, which we somehow have to invent. This is our free parameter. It describes the combined action of the cell of the enzyme. So okay, so here you have your growth rate. So this is basically, it has in a way somehow your Lagrange multiplier for the mass rate, and it depends basically on the pressure. So it's basically the trace of the stress of the Mendel stress tensor. Actually, it's localized with this localization function to the growth zone, and then you have basically this arbitrary parameter for it. And then this is the remodeling rate, which depends on the deviatoric part of the Mendel stress, which is also localized, and where you have basically then the remodeling factor. And this is basically all our parameters. And then we just have to solve it, right? The local mass rate is limited by the global mass rate, but is driven by the trace of the Mendel stress, and so in a way, right, this gives you only a sensitivity, right? The global it gives you a sensitivity to the pressure, and yeah, that's basically it. So we take mechanical equilibrium with respect to the turbo pressure and the zeroing force, and then we apply the growth equations, and we have here this pulled back Eikonal equation for keeping the size of the zeroing constant, the size of the growth zone constant in the final configuration, so in the current configuration. So this is then Patrick came up with this time discretization, which is basically a staggered scheme, which he learned in Berlin, and we also used a Huber-Gisow principle for making the discretization a bit better behaved. So this is another trick, and we had to use yet another trick. We also used an ALE method to carry the mesh, because when you form the septum, you get all the grid points, of course, into a small zone. So you drag it on with a growth tensor, and on top of it, you have to actually periodically remesh the entire thing. Only then you can solve it in a reasonable way. And so, unfortunately, I cannot show you the video for it, but it turns out that we can reproduce the fluorescence microscopy data for the growth pretty well, and we obtain the correct shapes as well as per the electron micrographs. And what is even better is that because we have only like 1.5 free parameters in it, we can adjust it, and we can even model the mutants. So if we just change the remodeling rate, we obtain the mutants as well. And that's basically all from this. Yeah. So if you want to read about it, it's all published, at least in form of preprint now.